Welcome to WikiPodcast. This is the deep dive, and today we're diving deep into something you interact with every day, probably without even thinking about it. Magnetism. It's this incredible force, that makes objects attract or repel each other, and it often works through this invisible magnetic field.
Right.
We've pulled together a stack of sources, articles, research, notes to really try and understand this fundamental part of physics.
That's right. And our sources make it clear pretty much from the get-go that the magnetism isn't some isolated thing.
Okay.
It's actually one side of a much bigger coin, intrinsically linked to electricity. Together, they form what we call electromagnetism, which is one of the universe's fundamental forces.
Yeah.
And at its heart, magnetism usually comes from moving electric charges.
Okay, let's unpack this then. Our mission in this deep dive is to cut through the complexity and really pull out the core insights from our sources. We want to understand what magnetic fields are, how those familiar north and south poles work, what creates the actual magnetic force you feel, and crucially, how it all connects back to electricity. We're here to guide you through the essential knowledge so you can be well informed about this invisible force shaping your world.
So the sources laid out pretty clearly. Magnetism describes these physical properties that objects exhibit because of a magnetic field.
Right, the field itself.
Exactly. The field is kind of the mediator, the thing that causes the attraction or repulsion.
Got it. Like, my fridge magnet or the needle on a compass. So what actually makes that magnetic field? What did the sources say?
Well, the sources point to a few key origins. The most fundamental are electric currents, literally moving electric charges,
Okay.
and also the intrinsic spin magnetic moments of elementary particles, specifically electrons.
Spin, like they're actually spinning.
You can kind of think of it like that, yeah.
Yeah.
Like a tiny built-in magnet that each electron has. And also, interestingly, changing electric fields can create magnetic fields, too.
Oh, okay.
But for materials we actually interact with, the magnetic properties come mainly from those electrons within their atoms, both their spin and their orbital motion around the nucleus.
Okay, so tiny spinning electron magnets are a big part of it. And when we think of a magnet, like in everyday life, we're usually talking at something that sticks really strongly, right? Like iron.
Exactly. Yeah, that strong effect comes from materials called ferromagnetic substances.
Ferromagnetic.
Yep, iron, cobalt, nickel, and their alloys. Those are the classic examples our sources mention. These materials are strongly attracted to magnets, and they can actually become permanent magnets themselves if you expose them to a strong magnetic field.
Right. But the sources also talk about other types of magnetism because, my aluminum foil doesn't stick to the fridge. Neither does a pencil.
Right, good point. That's because most everyday materials show much, much weaker forms of magnetism. So there are paramagnetic materials, like aluminum or oxygen. They're weakly attracted to a magnetic field. Then there are diamagnetic materials, copper, carbon, things like that, which are actually weakly repelled.
Repelled? That's weird.
It is a bit strange, yeah. And then there are antiferromagnetic materials like chromium, which are even more complex. But the effects for para and diamagnetism are usually so faint that, at everyday life, we just call these materials non-magnetic.
Gotcha. But technically, everything has some kind of magnetic property.
Pretty much, yeah. At a fundamental level, every substance does. It just might be incredibly weak.
So the magnetic field is kind of the star of the show here, doing all the attracting and repelling. How does it work? Does this field just fill space?
Yeah, essentially. The magnetic field permeates the space around whatever its source is, whether that's a moving charge, an electron spin, or a permanent magnet made of that ferromagnetic stuff.
And how far does the magnetic force actually reach? Does it just go on forever, getting weaker and weaker?
Precisely. The strength of the magnetic field, and therefore the force it can exert, always decreases with distance from the source.
Okay.
It can extend indefinitely, in theory, but its practical effect drops off pretty quickly as you move away.
Right. And what affects the field? Is it always the same shape and strength?
No, definitely not. The field's strength and shape depend on several factors the sources outline. Things like the strength of the magnetic source itself, it's a magnetic moment, the physical shape of the object creating the field, the amount and direction of any electric current flowing, and even temperature can affect it.
Okay, let's take a step back because this is where it gets really interesting, I think. The history. Our sources trace this stuff back thousands of years.
They really do. It all started with simple observation in the ancient world. People noticed certain natural stones, lodestones they're called.
Lodestones, right, pieces of magnetite.
Exactly, magnetite. They noticed these could attract iron. And the word magnet itself, it comes from the Greek magnetis lithos, meaning Magnesian stone, apparently after a region where these stones were commonly found.
I love thinking about those first discoveries. Our sources mention figures like Thales of Miletus in ancient Greece thinking about this.
Hmm.
And there's even that fascinating detail about an ancient Indian text, the Sushruta Samhita, mentioning using magnetite to help remove arrows.
Yeah, that's a great example of a really early practical use, and China played such a crucial role, especially with navigation.
Right, the compass.
Yeah. The earliest literary mentions of magnetism are actually from ancient China, and the first record of a lodestone attracting a needle dates way back to the 1st century AD.
And it was the Chinese scholar Shen Ku, right?
No, no,
The 11th century.
that's the one. He really nailed the understanding of using a magnetic needle compass, and he realized something important. The needle didn't point exactly to geographic north.
Ah, magnetic north.
Exactly. It pointed to a magnetic north pole.
Hmm.
Understanding that difference, the concept of true north, really improved navigation. By the 12th century, magnetic compasses, sometimes shaped like little spoons pointing south, were being used for seafaring.
Amazing. And in Europe.
Well, the understanding developed a bit later there. Alexander Neckham described the compass in Europe in the late 12th century. Then Peter Peregrinus wrote the first really detailed scientific treatise on magnets back in 1269, describing poles and how to find them.
Okay.
But maybe the most groundbreaking figure was William Gilbert. In 1600, he published De Magnet.
De Magnet, right.
He did tons of experiments and concluded something revolutionary. The Earth itself is a giant magnet.
Wow. So that's why compasses work.
Exactly. And finally explained it, moving away from older, more mystical ideas.
That really sets the stage for the biggest leap in understanding, doesn't it? Because for centuries, magnetism was just magnetism, attraction, repulsion, compasses. But then came the discovery that linked it fundamentally to something else entirely: electricity. This feels like a huge turning point.
Oh, absolutely monumental. The sources really highlight 1819 as a key year. Hans Christian Ørsted, he discovered, almost by accident, that an electric current running through a wire could actually deflect a compass needle nearby.
Just like that, an accident.
Pretty much. It proved that moving electric charges create a magnetic field.
Wow. An accidental twitch of a needle leading to a whole revolution in physics. It's amazing how these things happen sometimes.
It really kicked off a wave of discovery. Shortly after Ørsted, you had scientists like Biot and Savart developing mathematical laws to calculate the magnetic field produced by currents. Ampere did systematic experiments measuring the forces between wires carrying electric currents.
Okay, so electricity makes magnetism.
And then, the other side of the coin. In 1831, Michael Faraday discovered electromagnetic induction.
Faraday, right.
He showed that a changing magnetic field can induce an electric current or voltage in a wire loop. This is the principle behind electric generators, transformers. Basically how most of our electricity is made and moved around.
So, okay, hold on. We have electricity creating magnetism, that's Ørsted and Ampere. And then we have changing magnetism creating electricity, that's Faraday. What does this all mean when you put it together?
It means they're two sides of the same fundamental phenomenon. It was James Clerk Maxwell, building on all this work in the mid-19th century, who synthesized everything. He created a single, really elegant set of equations, now known as Maxwell's equations.
Maxwell's equations.
And these equations unified electricity and magnetism into a single, cohesive theory: electromagnetism.
Wow.
And the sources even mention Einstein's theory of special relativity here.
How does relativity fit in?
Well, relativity basically reinforced this unification. It shows that what one observer sees as maybe just an electric effect, another observer moving relative to the first might see as a mix of electric and magnetic effects.
That depends on how you're moving.
Kind of, yeah. Relativity essentially mixes electricity and magnetism, much like it mixes space and time into space-time. They aren't independent phenomena. They're just deeply intertwined aspects of this single thing: electromagnetism.
That is. Yeah, that's mind-bending. So even something that looks like just a magnetic field, like from a permanent magnet, is fundamentally connected to the electric side of things.
According to the sources, yes. Any change or disturbance in a magnetic field is always accompanied by a related electric field. And these changes propagate together at the speed of light as electromagnetic waves.
Like light itself.
Exactly like light itself. Light is an electromagnetic wave.
Okay, let's talk about the force you actually feel.
Yeah.
We've talked about fields and sources, but how does that invisible magnetic field actually push or pull on things?
Right, the force. This is explained by what the sources call the Lorentz force.
Lorentz force. Okay.
The core idea is, when a charged particle, like an electron or a proton, moves through a magnetic field, it experiences a force.
Makes sense.
Now, here's where it gets interesting and maybe a bit counterintuitive. This force, it's not in the direction the particle is moving, and it's not in the direction of the magnetic field either.
It's not. Then where?
It's always perpendicular to both the particle's motion and the field direction.
Perpendicular to both. So, sideways.
Exactly. Think of it like a sideways push. This sideways push is why magnetic fields are so good at making charged particles curve or spiral. It's crucial in things like particle accelerators or controlling plasma in fusion reactors.
Okay.
And the strength of this push, it depends on the charge of the particle, how fast it's moving, the strength of the magnetic field, and the angle between the particle's motion and the field.
A sideways push, that actually helps picture it. And the sources mention a way to figure out which way that sideways push goes, right? Some kind of rule.
Yeah, they describe the right-hand rule. It's a common mnemonic device, like a little hand trick you can use to determine the direction of the Lorentz force or the field or the velocity, if you know the other two.
Okay, handy. So back to those familiar north and south poles we learned about in school. Where do they fit into all this? We know opposite poles attract.
Yeah, so our sources describe the magnetic dipole as a very common and fundamental source of a magnetic field found in nature. It has those distinct north and south poles.
And a dipole.
And those labels, north and south. They originally came from using magnets as compasses. One end pointed roughly north, the north-seeking pole,
Right.
and the other roughly south, the south-seeking pole.
Makes sense.
And the classic rule holds. Opposite poles attract, like poles repel. But here's that surprising fact the sources highlight, related to the Earth's magnetic field.
Uh-oh, what now?
Because the north-seeking pole of your compass needle is attracted towards the Earth's magnetic pole up near the geographic North Pole.
Yeah.
That Earth magnetic pole, the one near the North Pole, is actually a south magnetic pole in terms of its fundamental magnetic polarity.
Wait. The Earth's north magnetic pole, the place compasses point to, is physically a south pole.
That's what the physics says. It's completely counterintuitive, isn't it?
Yeah, my brain just did a flip.
But it makes sense if you just think about attraction. The north end of your little compass magnet is drawn to a magnetic south pole.
Okay, I think I get it. Wow.
And the sources explain that magnetic systems naturally tend to move towards configurations with lower energy. This is why, for example, those tiny magnetic regions inside a ferromagnetic material.
Magnetic domains, you called them.
Exactly, magnetic domains. Think of them as little packets of aligned electron spins. They'll snap into alignment with an external magnetic field because that's a lower energy state.
And if they stay aligned?
You get a permanent magnet. And diamagnetic materials, they do the opposite. To minimize energy, they align their tiny induced dipoles against the external field, which leads to that weak repulsion we talked about.
Speaking of poles, this brings up one of the most intriguing theoretical ideas mentioned in the sources. Can you have just a North Pole all by itself? Or just a South Pole? Can you actually split them apart?
The million-dollar question. According to our sources, and well, all observations so far, no. If you take a bar magnet and cut it in half, you don't get an isolated North Pole and an isolated South Pole.
Yeah.
You just get two smaller magnets, each with its own North and South Pole.
Huh. So they always come in pairs.
Always, as far as we know. This is a really fundamental difference from electric charges, right?
Right.
You can easily have an isolated positive charge, like a proton, or a negative charge, like an electron.
Sure.
So this lack of isolated magnetic poles in nature has led to this theoretical concept of a magnetic monopole.
A monopole, meaning one pole.
Exactly, an isolated magnetic pole, basically with magnetic charge, kind of analogous to electric charge.
So a magnetic monopole would be like the magnetic version of a single electron charge.
Yes, precisely that.
Yeah.
But despite physicists searching for them for decades, ever since Paul Dirac first theorized about them way back in 1931,
Yeah.
the sources state flatly they've never been observed. Their existence is still a totally open question. They might simply not exist in our universe.
Wow. Okay. But why are people looking so hard? Is it just curiosity?
We're partly. But here's a mind-blowing detail from the sources. Dirac showed that if magnetic monopoles did exist,
Yeah.
it could actually explain why electric charge is quantized.
Quantized, meaning it comes in packets.
Exactly.
Huh.
Why electric charge comes in discrete packets, like the specific charge of an electron or proton,
Yeah.
instead of being able to have any old continuous value.
So The existence of this hypothetical magnetic thing could explain a fundamental property of electricity we do see.
That's the theoretical link. It's fascinating. Some grand unified theories in physics actually predict monopoles should exist, but then you have the problem of explaining why they'd be so incredibly rare if they formed in the early universe. It's still a big puzzle.
That connects magnetism to the deepest questions in particle physics and cosmology. That's wild. We touched on the different types of magnetism earlier: ferromagnetic, paramagnetic, diamagnetic. Our sources hinted that understanding why materials behave differently needs more than just classical physics.
Yes, absolutely. That's where quantum mechanics really comes into play.
Hmm.
While classical ideas, dipoles and fields, get us pretty far, a full explanation for why electron spins line up so strongly in ferromagnets, or why some materials are weakly repelled, that really needs quantum theory.
Okay. What's the key quantum idea?
The sources mention something called the exchange interaction.
Exchange interaction.
Yeah. It's not like two tiny magnets physically pulling on each other in the classical sense. It's a purely quantum mechanical effect. Think of it as a powerful sort of quantum rule or preference that dictates whether the electron spins in neighboring atoms strongly prefer to align parallel to each other,
Okay.
which leads to ferromagnetism and paramagnetism, or antiparallel, pointing opposite ways.
And anti-parallel leads to?
Antiferromagnetism, where they cancel out, and it also contributes to diamagnetism. In ferromagnets, this exchange interaction is so strong that it forces spins into parallel alignment over large regions, creating those magnetic domains we talked about, even without an external field.
Until it gets too hot, right? The Curie temperature.
Exactly. Thermal energy eventually overcomes the exchange interaction above the Curie temperature, and the alignment breaks down.
So that quantum rule is basically what makes a fridge magnet stick so strongly. It's not just tiny magnets interacting.
That's the gist of it, yeah. It's much, much stronger than the classical magnetic dipole interaction between individual electrons would be on its own. It's the microscopic quantum origin of these big macroscopic magnetic properties like ferromagnetism.
Got it.
The sources also briefly mention other types, like ferromagnetism. That's where neighboring spins are anti-parallel but have unequal strength, so they don't quite cancel out, leaving a net moment. And superparamagnetism, which happens in really tiny ferromagnetic particles.
Okay, fascinating stuff. Let's bring it back down to Earth a bit to a really practical application mentioned everywhere: electromagnets. These are in tons of technology.
Oh, absolutely. They're everywhere. An electromagnet is, well, simply a magnet where the magnetic field is produced by an electric current.
Simple concept, big impact.
Right. The key feature is that the magnetic field exists only when the current is flowing. Turn the current off, the magnet turns off.
Which is super useful.
Totally. They're usually made by winding wire into coils, often wrapped around a core of ferromagnetic material like iron, to greatly concentrate and strengthen the field.
And the big advantage is you can control the strength, right?
Yeah.
Just by changing the current.
Exactly. That's their main, plus controllable strength and the ability to switch them on and off instantly. The downside, obviously, compared to a permanent magnet, is they need continuous power to keep that field going.
Makes sense. And the uses.
Oh, the sources list countless uses: electric motors and generators, loudspeakers, hard drives, relays, those big scrapyard cranes lifting metal.
Right.
And of course, really high-tech stuff like medical imaging devices, MRIs. Those use incredibly powerful electromagnets.
That MRI connection is a perfect example of powerful, controllable magnetic fields. Wow. You also mentioned something about magnetism in living things that seemed kind of unexpected.
It is surprising, isn't it? The sources discuss magnetoception, the ability of some organisms to actually sense magnetic fields.
Like birds navigating.
Exactly, that's the classic example. It helps them navigate. And yes, ferromagnetic materials, specifically magnetite again, have actually been found in living organisms.
In animals?
Yep. From the teeth of certain marine mollusks called chitons to bacteria, birds, insects, and even found in tiny amounts in human tissue.
In us. Do we know why?
Well, the function in humans isn't really fully understood yet. But in many animals, it seems pretty clearly linked to their navigational sense, their internal compass. And you remember that wild fact the sources mentioned about water?
Oh yeah, water being diamagnetic, the levitating frog.
Precisely. I mean, water's only weakly diamagnetic, but in extremely strong magnetic fields like the ones from those huge research electromagnets.
Yeah.
The diamagnetic repulsion can actually be strong enough to levitate things that contain a lot of water, like a frog. It really demonstrates that subtle magnetic effect on a visible macroscopic scale.
That's incredible. Just floating there because water is slightly repelled. Wow. So, okay. From ancient rocks that mysteriously pulled iron to this deep fundamental connection with electricity, explaining everything from how our compasses work to high-tech MRIs and even uh, levitating frogs.
Yeah.
Magnetism is just this incredibly rich and fundamental part of our
It
universe.
truly is. And as our sources really highlight, understanding it fully takes you on this journey from
Mm.
everyday observation through electromagnetic theory and right into the weirdness of quantum mechanics,
Yeah.
where concepts like that exchange interaction finally explain the fundamental why behind how different materials behave magnetically.
And the fact that we still haven't found those magnetic monopoles,
Hmm.
even though theory suggests they could explain something as basic as why electric charge comes in those neat little packets, it just leaves us with this powerful reminder, doesn't it? That even with a force we think we know so well, there are still these profound mysteries just waiting to be uncovered.
Absolutely. A great point to ponder, really.
Yeah, it really is. Well, that's our deep dive into magnetism for today. Thanks for listening. Write us your opinion in the comments on what you found most surprising about magnetism or its connection to electricity. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.